Hello, and welcome to Willow Waves, a student-produced podcast that brings together young minds to explore and discuss current events and topics that connect all of us.
Hi, I'm Asa.
I'm Eva.
And I'm Wyatt.
And today we're interviewing Brian Huber from the Smithsonian Museum of Natural History. We wanted to ask you some questions for an interview today.
Sure.
All right, I will start off. What was Earth's climate like during the Cretaceous period?
Well, we've got ways to estimate temperature of the Earth through time. And one of the ways is through the chemistry of shells, looking at the isotopes of oxygen. And there's an isotope oxygen 18 and an isotope oxygen 16. And the ratio of those two isotopes is directly related to the temperature of when the shell formed. So if you can get the ratio from the shell, you can get the temperature. And so a lot of what I've done is reconstruct temperatures through time from the tiny things I study called foraminifera. And what the data tell us is that the Cretaceous, it was a very warm time. In fact, in Antarctica, where it's freezing cold, of course, during the Cretaceous, it was very warm. And we know that from the temperatures of the ocean, from the foraminifera shells, but we also know that from studying the rocks and determining that there were a lot of forests down in Antarctica during the Cretaceous time. What's in Antarctica right now? What covers Antarctic continent?
Ice.
Ice, yeah. Almost 2 miles of ice in the middle of Antarctica, right? And during the Cretaceous, Antarctica was forest cover, and guess what? There were also dinosaurs in Antarctica during the Cretaceous. And dinosaurs are reptiles, and they don't like it when it's cold typically, right? Well, we assume so. They're not around today, but that's what we assume, right? Yeah, so our evidence shows this is what we call a hot greenhouse Earth.
How were the oceans different in the Cretaceous period compared to now?
Well, today, the very bottom of the deep ocean is about 1 degree centigrade, 1 to 2 degrees centigrade. During the Cretaceous, the estimates we get from the bottom living foraminifera called benthic foraminifera give us temperatures as warm as 20 degrees centigrade. So that is really warm compared to today, huh? And so those warmer oceans, the warmer the ocean is, the less oxygen that it can hold. There's less dissolved oxygen in oceans. So during the hot greenhouse of the Cretaceous, a lot of the ocean in certain times had very little oxygen on the ocean bottom. And so this is what's called an oceanic anoxic event. And so these things were worldwide for various periods of the Cretaceous ocean.
That sounds really cool. Were there any weird giant creatures back then?
Yeah, well, in the ocean, there were what were called mosasaurs and also plesiosaurs. These are swimming reptiles. And as you know, the reptiles evolved from ancestors on land, right? But there were abundant fish in the ocean, and reptiles evolved first to just start swimming and catching fish and things and coming back to shore. But then they evolved to live fully in the ocean. And plesiosaurs have really long necks, and they were very long animals. They went after sharks and various other fish, and also things called ammonites. So did mosasaurs. And so these things were quite vicious. We've got beautiful skeletons of plesiosaurs and mosasaurs at the Natural History Museum. Foraminifera are single-celled organisms that live in the ocean today, and they make a shell, and the shell becomes part of the fossil record. So when the organism dies, there's two kinds. First of all, one kind floats. It's called planktonic, enters in the sediment, and the sediment accumulates with time, right? Because with time, different shells and clay and other sediments accumulate by falling through the ocean, right? They come to the seafloor and the sediment builds up. And so these foraminiferal shells are really valuable because they are used to identify species. Different species lived at different geological times. And so when you can identify the species, you can determine the age of the sediment. So some planktonic foraminifera have very short age ranges. So, for example, in the Campanian age, there is a species, and this is in the late Cretaceous, there's a species called Radiotruncana calcarata. It's a very distinctive form. That species lived for only 1 million years, which to you sounds like a really long time. But actually, when you consider that it lived between 76 and 75 million years ago, that really helps you identify the age of these really, really old sediments, right?
Yeah.
So just by seeing and identifying that species, you know what geologic age you're in. And so some other species might have an age range of 5 million years. But when you're looking at a sample from the ocean cores that I look at, for example, you're looking at an assemblage of different species. And by understanding the overlapping age ranges of the different species, you can really narrow down the age of the sediments. So they're really useful for that.
That sounds cool. Final question from me. How do tiny fossils like foraminifera help scientists figure out how old rocks are?
Well, you tell me. I just explained that. So you tell me what I just explained.
It shows you what time period you're in.
Yes.
How long they live.
So the species are distinctive, right? They have particular morphologies.
My question is, what is biostratigraphy and how does it help us put together the timeline of Earth's history?
Well, biostratigraphy is using fossils to tell geologic time. And so what I just talked about with identifying different foraminifera species to tell the age, that's biostratigraphy. And so when you're using multiple species and identifying their presence in a sample, that tells you that they were alive at the same time. By knowing the age range of when they were alive, you can get the age of the sediments.
That's pretty cool.
How did planktonic foraminifera evolve during the Cretaceous and what caused some of them to go extinct?
Well, that's a good question. So the Cretaceous is a very long time. It goes from about 142 million years ago to 66 million years ago. And during that time, there's a lot of evolution of foraminifera. Cretaceous has the word creta in it. Creta in French means chalk. So can you guess why the Cretaceous was named that?
There was a lot.
Because there's lots of chalk in the Cretaceous age. And chalk is mostly made up of the shells of foraminifera and another form that has calcium carbonate called calcareous nanofossils. So chalk is full of calcareous nanofossils and foraminifera. And they evolved over that time from 142 to 66 million years ago. And they increased in diversity. They increased in their abundance worldwide. And at the end of the Cretaceous, they became extinct. Do you guys know what caused the extinction of dinosaurs?
Meteor.
An asteroid, which is a large meteor.
Yeah.
So an asteroid is anything that's, I think, is bigger than 100 meters in diameter is an asteroid. So an asteroid that hit the Earth 66 million years ago was 11 kilometers in diameter, 11 kilometers, traveling at 44,000 miles per hour. Can you imagine how much heat energy and how much the shock energy was when that hit the atmosphere?
12 tons.
It's huge, huge. And so it caused forest fires all across the continents, and it caused a huge ejecta cloud that blocked out sunlight.
Wait, did it make like
And so, what's that?
Did it make like a toxic air like thing?
Yes, and so it also caused a lot of sulfur to go up in the atmosphere and acid rain. So the sunlight was blocked out. You get all this sulfuric acid that comes in the ocean, and the plants can't live without sunlight, right?
Yeah.
what happens to the plants?
They die.
Are there plants in the ocean?
Yep. Some.
There's algae, right?
Yeah.
So there's also phytoplankton like diatoms and calcareous nanofossils. Without sunlight, they have no energy and they die. Well, guess what? Foraminifera feed on calcareous nanofossils. They feed on tiny plankton algae. Guess what happens to the foraminifera?
They died.
They can't feed anymore, right? So they die. And so we have a big, over 90% of species of foraminifera went extinct at the end of the Cretaceous because of the asteroid impact. And so that's a pretty huge change, isn't it?
Yeah.
What happened to ocean life when the dinosaurs went extinct? Did the tiny ocean creatures survive?
So I just answered that question. What do you think?
Explosion. Explosion. Explosion.
Do you remember what I said? What percent went extinct?
90%.
Which means 10% survived, right?
So they did survive.
Yeah, some did survive, right?
Ow.
And so the ones that survived, they had kind of a weird life. They were mostly plankton, but they could also adapt to live on the ocean bottom for a little while. They could find organic matter in the ocean sediments. Also, new species occurred after the asteroid impact. And in fact, some new species evolved from benthic ancestors, and they went up into the plankton. Okay?
So now it's my turn. What do strontium isotopes tell us about ancient oceans and climate? That's mine.
Strontium isotopes are measured, I think it's 87-86 strontium ratio. It's an isotope that varies depending on the amount of erosion from land of sediments into the ocean. So it's really driven by major long-term changes in climate. Strontium has a very long residence time in the ocean, and by measuring the ratios of 87-86 strontium, you can get what's called a strontium isotope curve through geologic time. So we have this curve that's been developed by measuring sediments around the world, and this strontium isotope curve is used as a guide to compare with strontium isotope measurements from particular samples. By determining the ratios of strontium isotopes in particular samples, you can get an estimate of age. So it's very useful for determining age of sediments.
Sounds cool.
Why do scientists study past extinctions? Can it help us understand changes happening in the ocean today?
Yes, for sure. So, for example, we look at different times of climate warming and climate cooling. And the question is, well, how tolerant are species to these kinds of climate changes? And the Earth is a very big place, of course. The ocean is very big. And so you might get cooling in certain regions, but then, a lot of organisms might be able to migrate and move to other parts of the ocean. However, there's thresholds. When it gets too cool, the organisms can't adapt and they become extinct. And so what we look at are what are the climate thresholds to find out the tolerance limits, which gives us insight to what modern day tolerance limits are for the oceans that are around, for the organisms around today.
And our very last question is, if you could travel back to the Cretaceous for a day, what would you want to see or study?
Well, I think all of us are really curious what it would be like with dinosaurs around. And especially the very large sauropods, the huge Apatosaurus, right? I mean, wouldn't it be so cool to be sort of somewhere in the forest edge looking out at a giant river and seeing these huge sauropods like Apatosaurus walking around? And then hearing something like Allosaurus in the background screaming and, going after some kind of prey. I wouldn't want to be there without being protected somehow, though, right?
I would see why.
So the Cretaceous world to me is just such a different world. I'd love to get transported back in time and see what it was like. Like, think of pterosaurs flying around, these giant reptiles, flying reptiles. Can you imagine a 20-foot wingspan giant reptile flying around over your head?
I'd be so scared.
Yeah, pretty wild.
Yeah, that's all the questions we have for you. Is there any extra information you'd like to give us?
Oh, well, Wyatt's been to the museum a couple of times. I don't know if you guys have, but come on down to the museum. We have a beautiful fossil hall, and I worked on Ocean Hall. There's actually the foraminifera in the Ocean Hall, and in fact, I feature the story of the asteroid impact and the extinction in the Ocean Hall, so you could come and find that.
This is Asa, Eva, and Wyatt signing off. Remember to tune into Willow Waves. You never know where our next adventure will take us.